Hello, we are back today continuing the review session for the Quiz 5 take-home for Organic Chemistry 2 in Jon Baker's class at VCU. It is now May 1st, May 1st, and we have the ACS on Thursday, so let's kick this thing's butt, okay? So the first question that we have, I'm going to zoom in so it's clearer. For some reason, the second page is a little bit blurrier, but you have a benzene, which you remember is aromatic, and it's been substituted with chloromethane. It's got one carbon, so it's methane, and then there's a chlorine on it. So the first reactant that we have is KCN. And if you remember back to chapter 6 in Christine's notes, KCN is one of our, it's nitrile, and it's one of our strong nucleophiles that's a weak base. So on methyl primary and secondary alkyl halides, it's going to perform an SN2 reaction. On a tertiary alkyl halide, it's not going to do anything. Like, it's not going to be able to, well, I mean, it may be able to do Ne2, I believe. Nope, no reaction. Okay, so with this question, what we're going to do is we're just going to kick that Cl off, and we're going to replace it with a nitrile, which is C triple bonded to an N. So I'm going to go ahead and draw that in right here after that first step. Remember, if there was any stereochemistry right here, this Cl would end up flipping its directionality. Okay, so now you have this, and there's two carbons there. So now it's gone from a one carbon substituent, the chloromethane, to a two carbon substituent. And this is important that you count your number of carbons and you remember that this is going to be here. The next thing that we have is H2PD. I believe for triple bonds, that was chapter 9. We originally saw it in chapter 8 for alkenes, but all this is catalytic hydration. I believe it was in the amine chapter as well, we covered this. But when you hydrogenate this, you're going to completely saturate that triple bond to make it a double bond between this guy, and then you're going to have your two hydrogens there, single bond, and then this is going to become NH2. So now it's completely saturated. That's where you are after step 2. And then I'm going to draw this out. Anytime you see C6H5, understand you're looking at a phenyl substituent. So that's just the benzene that's connected. I'm going to draw out what number 3 is so that we can proceed with this reaction. C6H5. There's one COCl. Okay, now I'm going to look at what I have here. I have a primary amine right here, and I have an acid chloride. Amines and acid chlorides are going to do an acylation reaction. Again, I think this was chapter 19 and 21. Yep, acylation of amines. So what that's going to do, this is basically, you can think of this whole thing as an R group, right? And what this is going to do, let me move my camera down, is it's going to kick off this Cl right here, and then you're going to get that like this, and that's it. And you're going to lose hydrogen, obviously, in this process. I don't know if I'm, you don't need to draw the everything, but because it's a major organic product. So this is somewhat close to what you're going to be getting. Just remember to correctly draw in that R group. Don't double anything up. Yep. And then moving on to the second question, which looks like it's got a lot going on. The first thing I'm going to do, just to avoid confusion, is draw this guy out. That's a nitro on an ethane. And remember that nitros are basically equivalent to 2 carbonyls. So when you have an alpha hydrogen here, you have 2 of them here, what you are able to do is essentially work with this as if it is a beta dicarbonyl alpha hydrogen like you had seen in chapter 22. And if you look at this one here, this is an ester, and there are no available alpha hydrogens to this ester, so we're going to be doing a mixed Claisen reaction. It's Claisen-esque. So what's the first thing that's going to happen? The negative charge on this is going to come over, it's going to grab a hydrogen, and it's going to put a negative charge on this nitrogen. Or not this nitrogen, it's going to put a negative charge on this carbon right here, and that's our enolate ion. And then what it's going to do, because there's a partial positive right here on this carbonyl, it's just going to come in and it's going to attack. You're going to get this whole thing is going to loop back down, and this guy's going to pop off. And let me see what the steps are after that. Okay, so then I'm going to draw what our product is, because we have a second portion to this reaction that we need to be able to do. I'm just going to erase this super quickly. Well, I hope that it's quickly. Okay, now you have this, and this is just a CH3 here that was on this guy. It's that same CH3. What you have here still is a sort of pseudo, it's not a carbonyl, it's an NO2, but it's a pseudo beta dicarbonyl alpha hydrogen that's available. So this one, because you're still in acidic conditions, is going to be able to be popped off by this guy like this, and then you're going to obtain another negative charge right there on that position. So I'm going to draw that in as well. I'm just going to use red to draw the negative charge. So you see, okay, now I have a negative charge. So what are my next things in the reaction that are going to happen? If I go over here and I look at my reactants, I have CH3, CH2, Cl. Again, I am not really able to work that well with just things written like that. So I'm going to draw what this is. It's CH3, CH2, Cl, like this. Well, what do we have here is a negative charge, which means the negative charge in this carbon is able to work well as a nucleophile, right? It's negative. It's seeking positive charge. It can go over right in here and do an SN2. Take off that guy and then attach this group here. Remember to count your number of carbons when you do the step. You are adding 2 carbons, okay, to this position right here. Don't just do it like this, right? Don't think, oh, I'm just going to attach that section here. No, make sure to count the number of carbons and that you get it as it's supposed to be. And that's going to be what's happening. That last step is just an SN2 using the enolate nucleophile that you got from the mixed Claisen reaction. Again, this is a mix of chapter 22, and it's going to be a mix of chapter 6 all the way back just to SN2s. So that's it. We can move on to the next one. Looking at the next one, it looks like it's a little bit complicated. We have an ester here. Looking at it, I recognize that I have a base in ethanol, or not ethanol, I do have a base in ethanol. I have a base that's pretty strong, and I have alcohol, and I have positions with alpha hydrogens, so I can just go ahead and do the same exact thing that I've been doing in these past reactions, which is from chapter 22. So one of these hydrogens right here, I can just take it, abstract the proton using the base, and this bad boy transforms into a CH2 minus, well actually that negative charge needs to be on the carbon. So we have a negative charge that we've gained there from that first step. Now, what do we have right there? Well, I think that it's important that we understand that an intramolecular reaction is more likely to occur in this one because these guys are locked and they're positioned right next to each other. So this negative charge is going to be right next to this partial positive of the carbon on the carbonyl. They're neighbors. They're just going to magnet right together. This guy's going to go in here and you're going to form a ring. So when making sure that you have the right number of atoms in this ring, it's going to have 1, 2, 3, 4, 5. So you're going to draw a 5-membered ring, and make sure that you keep your, so you draw your 5-membered ring, and when this guy comes in right here, you see the same thing that you usually see with esters. This guy is going to come right back in like that, and it's going to drop off. And I'm showing this all as one step, but understand that this is kind of like 2 steps. I'm just drawing this one because we know that carbonyl is going to be reformed and that OR group is going to pop right off. Again, as it did before, the OR group leaving when it takes a proton somewhere is going to just reform the ethanol that we had, which is, again, pretty great. So once we get there, where am I? I'm making sure I do this correctly. Then what's going to happen is it is still in basic conditions, and the ring that you have, it's going to have something like this on the end, right, and then it's connecting here. It's going to have a hydrogen here again, and that hydrogen is still in basic position. That hydrogen is still in basic conditions. Again, this is a beta dicarbonyl hydrogen, chapter 22. That base is going to continue to take this guy and plop a negative charge on right here. So in order to avoid that from happening and maintain our final product, the last step that has been included in this reaction is hydrogen. And that's just to make sure that you reprotonate your product and you don't kick that reaction forward again. Then our next question, I see immediately 2 very important things. I see a beta dicarbonyl hydrogen, and I see a conjugated system here, a conjugated ketone. So I'm just going to write down what I see to get it out in case I might need to remember something about it later. Conjugated ketone. This is going to go into one of those problems that we haven't actually practiced in class yet, at least I don't think we did, and that was Michael addition. And what it basically is just conjugated addition. What happens is, okay, well first let me form our enolate. There is a hydrogen here. I want to make a note of this. There is a hydrogen at this position, and there's a hydrogen at this position. But this one is between 2 carbonyls. This one is just next to 1 carbonyl, and it's, when you're talking about acid-base, the acidity of this one is much stronger, so this is the one that's going to form the enolate. That being said, this guy, gonna come over, take this, and then I'm just gonna redraw that as a negative charge right here, okay? So we see that we have our enolate. Bam. Okay. And now, what Michael addition does is it's going to be, I think, basically 1,4 addition. Okay, actually no. It's just going to go over and it's going to add to this end of the conjugated system, and then it's going to saturate this one with hydrogen. Just like that. And then whatever this R group is going to add right there. So make sure to count your number of carbons. Make sure you don't forget either of these guys. And that's it. It's actually not too complicated. But yeah, make sure to count your number of carbons. As always, just redoing it recounting them is going to help you avoid what could be a right or could avoid a wrong answer. Avoid getting confused and just being able to really easily eliminate the wrong answers in the ACS. So that is pretty important. And that product wasn't followed up by anything, so that would be our final product. This next question I actually thought was pretty fun. We start out with a 1, 2, 3, 4 butanoic acid. I'm just going to name this. And we know that this is a carboxylic acid. So one of the hints that we can say is carboxylic acid. Something's happening, it's going to be a sequence. I maybe should be thinking about acid derivatives. So keeping that in mind, let's go over. We see there's 3 steps that are going to happen, and then we're going to have 1, 2, 3, 4 carbons, right? And it's going to be just a straight chain nitrile. So we did not add any new carbons. In order to do that, what we're going to be thinking about is, okay, well, what can I do to go down this acid derivative chain? This is going to be chapter 22. And one of the first things that we can always do with an acid is thionyl chloride. We can turn this into an acid derivative, and then we have something that we can kick off. So thionyl chloride was SOCl2, and then we can turn this into an amide. And that's a little bit strange. So you're thinking, like, why would I want to turn this into an amide? I'm trying to get this here. Well, amides do have the nitrogen in there. It's only going to attach a nitrogen onto the end of this chain here, right? So you're still going to have 1, 2, 3, 4 carbons. You're going to have a nitrogen there. So maybe I can attach an amide. And then if you had, there's going to be no R groups on this. So why not use ammonia? Using ammonia, you're going to have acylation of amines. Acylation will also work on ammonia. So we're going to have this chain here, O, and then it's going to be NH2. And then what we haven't, I don't think we've gone over, we may have, there's a very special reactant that can just do this. This is that lasso-chemistry that you talked about, where it's removing water. It's going to grab these 2 hydrogens, it's going to grab this oxygen, and it's going to reduce this amide to a nitrile. And we're not using LAH. Remember that. We don't want to just like get rid of this carbonyl. We want to turn this into a triple bonded CN. So the special thing that we're using is in chapter 22, and it's called P2O5. I don't think that we've seen that anywhere else in the course. We may have, but adding P2O5 removes water from a primary amide and turns it into a nitrile. This is a type of dehydration, which we see we are losing water, we are dehydrating. Moving on to the next one. This looks a little bit complicated, but really what we have is it's an anhydride. I'm just going to write that down actually. Anhydride, we know something about properties of that. An anhydride is an acid derivative. And one of the properties about all acid derivatives is they can be hydrolyzed back into their carboxylic acid form. So what we can do is just turn these guys I'm going to redraw this. We can just turn these guys right back in. That's HOOC-COOH. Right back into our carboxylic acids. That's just what's going to happen, and it's super easy. I think writing down, okay, I recognize what type of molecule this is. That's a really great first step, saying what type of chemistry am I dealing with? Am I dealing with acid derivative chemistry? Am I dealing with amines? Am I dealing with alcohols? Am I dealing with substitution? Is this an alkyl halide? Is this a leaving group? Is this a thiol? It can really help you if you can start to just get the information about the product down, make it so it's way less confusing to try to navigate what is going on when I mix this chemical with this. So just recognizing that's an anhydride. Anhydrides are acid derivatives. That step, H3O+, that's aqueous acid, that's hydrolysis. Hydrolysis of an acid derivative is going to give you the carboxylic acid back. So I think that's really just super easy, like a super easy way of approaching problems in like a systematic way that's going to make it so you are way less confused on the ACS. Because I remember like the first time, or not first time, like my first ACS, that was organic chemistry, not organic chemistry, it was chemistry 1, like the first chemistry course, and I just wrote down as much as I possibly could during the test, and I wrote my heart out and dumped all the information that I could down, and it made it so I had like this sort of guide to reference as I was taking the ACS, and I didn't have to worry about forgetting something halfway through the problem, or maybe not recognizing something about a certain problem. So finally, we're going on a little rant there to our second to last problem, which is this one right here. This is a huge looking chemical, but we're going to, again, chapter 22, the only quote-unquote reactant, the only thing we're doing to this molecule is we're heating it. So what happens when you heat a compound with beta dicarbonyls is decarboxylation. And only the beta dicarbonyls are going to decarboxylate. So let's just go through this molecule and look at every single one of these to see if we can recognize where they might be. This is the alpha, beta, alpha, beta, alpha, beta. This one does not have any, so he's going to say the same. This one is alpha, beta, alpha, beta, alpha, beta. He's going to say the same. This one is alpha, beta. Oops, okay, that one's going to have some sort of reaction that happens. Alpha, beta. What am I doing? Alpha, beta, alpha, beta, alpha, beta. No, just two. I don't know why I said 3 times, multiple times in a row. And then here's our last one. Alpha, beta, alpha, beta. And that's it. This is the only one that's going to react. And when you decarboxylate, you're just turning this guy into an H group. I do want to go over this for the rest of the class and see maybe is there anything I may be missing to make sure that I'm not. But I think in the meantime that's all that's really happening is there's one group that's able to react with a beta dicarb or just a beta carbonyl. So beta keto carbonyl. No, beta 2, a carboxylic acid, beta 2 carbonyl. Sorry about the words there. Finally, we have our last problem. My first thing that I'm going to do is I'm going to, before even thinking about which group has priority, I see that there's like one really major parent chain that happens right here. So 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11. So it's 11 carbons on it. It is an undecane. I'm going to write that down. And then I'm going to consider what may have priority? So what will have priority here is going to be the ester right here. When you're naming an ester, when that has priority, this group right here, you're going to name that as a separate word. So before we name this molecule, that first word is going to be 1, 2 carbons, ethyl. So like if this was just like a methyl here, this would just be ethyl methyl or ethyl methanoate. So ethyl is going to be the first word. I'm going to write that down in green because we know that's coming first. Ethyl. Ooh, I want it to be green. Ethyl. Okay. And then right here we have an amine on the 5 position. So I'm just going to go through this carbon. I'll worry about alphabetizing later. I'm just going to write down every single part that I'm encountering. So right here we're going to have a 5-methylamine. You could also say 5N-methyl. I'm just going to write the parts that I have that I'm not sure where they go yet in yellow. So 5, oh sorry, I think it's not the right color. Okay, 5, I'm going to say ethylamine. Oh, sorry, it was not ethylamine, it was methyl. My bad, there's only 1 carbon, don't make that mistake. So that's going to be a methylamine. We could say N-methyl, we could say methylamino. So sorry about the mistake that I had made. So I'm just going to write that down. 5-methylamino. And we're not done with that portion of the molecule because we know that this is a chiral center. That's indicated by these dashed lines here. So we need to be thinking, is this R or S? So I'm going to clear off what's right here. And I'm going to redraw those dashed lines in. The most electronegative atom directly connected to this is the nitrogen. And she is going back. The next highest priority, these are the same, these are the same. This one's going to be different. So the next highest priority is going to be here. So I'm going to write 2 for second priority. The third priority one is going to be here. We don't really care about that. And the fourth priority one is coming forward, and that hydrogen. Draw that better. Hydrogen equals 4th. Okay, 1 equals N. You can try to look at this molecule from the other side in order to imagine how it's rearranged so you can get it correctly. But what I think is easiest is I know I want my highest priority one to be in the front so I can designate it R or S. If I just look at this as it is, and note that I put the wedge down here. Technically the wedge is like right here because it's tetrahedral geometry, but just forget that and just look at this. If I'm moving with my highest priority one in the back, if I'm moving like this, it looks like an S. Right? And I remember that because S, you're moving like to the left. Because it looks like an S, therefore, that's in the back, it's not how it's supposed to be, this is going to flip and this is going to be an R. So this is going to be R 5-methylamino. So now we've said stereochemistry there. We can move on down the chain. This next one that we have is an alkene at E7. So you have 2 options when you have an alkene. You can say EZ or you can say cis-trans. When it's only, like when it's like a regular alkene, there's no secondary like substitutions in each of them. It's just like hydrogen and a substituent, hydrogen and a substituent. You can name it as cis and trans, but you can't say cis and trans with this one because it is got multiple things coming off of it. So instead you're going to use the EZ terms. Baker had said this thing that I remember and I actually think is pretty good, was the opposite. So on each side of this, you're going to find out whichever one has highest priority. The oxygen is the most electronegative, so this is going to be the stronger one, and you're comparing this one to a hydrogen. So this one's going to have priority. So this is the next priority. These are on the opposite sides of the alkene, right? They're on the opposite sides, so this is going to be E. I'm going to write that. Well, and then we can say that it's E7. Let's insert it into this name, actually. So it was undecane, but you know that it's going to have a double bond here. It's going to be E, and it's going to be undec7ene. And I'm not going to finish this yet because I do, if I look at this here, it is an ester, so we're going to name it as an O8. So it's going to be 7-ene O8. Undec7ene O8, and it's going to be E, which I think you put at the beginning of the molecule name. Next, we have the substituent on this. There's no more substituents on this end. That's part of the parent chain. She's taken care of. And the next and last thing that we have here is, this one. So this is an ether. We have an oxygen, ROR. So for ethers, when we name them, we say whatever the smaller substituent is that's not part of the parent. This would be iso, because it's an isopropyl, or isoprop, and then you say oxy. So this would be, I'm going to name it over here. I know it's going to contain isopropoxy. Okay, so finally, we can put all of these things together. I know I have E undec7ene O8, and I have, oh, I forgot the number here. This was on the 8, so it's 8 isopropoxy. Okay, now we can get to clumping all of these names together. Make sure that you put them not in order of which number comes first, but alphabetic. So this I comes before M, so it's going to be ethyl. You're going to say your ethyl, and you're going to say RE, I think. It's going to be 8 isopropoxy, and then the 5-methylamino, and then this like final whatever it is, undec7ene O8. So that is the quiz, and we finished, and we survived, and we're gonna knock out the ACS on Thursday, and yeah. So I would, at this point forward, go through Christine's notes if you're using the textbook. If that's worked for you, keep doing whatever's working for you. But I would go through Christine's notes beginning at chapter 1 from last semester, Organic Chemistry 1. And I would start at chapter 1. I would write every single thing down. I would make yourself your own Quizlet. I have Quizlets that are available that you've gotten for the past 2 semesters. You can use those. I would also highly recommend making your own based off of stuff you feel like you just aren't getting, stuff that's like extra that you want to memorize, maybe special little rules that have helped you, or something that you keep like, oh, I keep forgetting this. I need to put this in like a massive major study guide for myself to make sure that I get it. And while you're practicing, I would go through your tests from Orgo 1 from last semester, and your tests and your quizzes from this semester, also quizzes from last semester. One other thing is, we'll actually go through them multiple times. do them, grade your own tests, like do a blank copy to the best of your ability, go back and grade it, and write down as you're grading on the side what the mistake was that you made. If it was something you didn't remember, put that in your Quizlet. If it was like some arbitrary mistake, I forgot to count my number of carbons, then make a plan for yourself that when you're approaching a question, you're going to double check, you're going to count as you're going, you're going to put an extra step into how you approach it to make sure you don't make that mistake again. I think that just having like a lot of discipline about your study habits, and this is going to make the biggest difference on Thursday and how well the ACS treats you. But don't worry too much about it, because there is a major curve that's going to be applied to it, because it's only graded out of 50 points and I think 70. So you have that going for you, and you can always, if you have to, it's not the end of the world, you can always retake the course or just study for it outside of this. If you're planning on taking the MCAT or something, take a course like Kaplan or Altreus or something to be able to really master this material and understand it. Finally, one very last thing that I've said throughout this is when I look at a problem, if I see that something's written out in like molecular formula, I'm going to draw that chemical so I see what I'm working with. And then when I see a chemical, whether it's one I've drawn or one that was provided to me drawn, what I'm going to do is I'm going to try to classify it. If it has carbonyls, I might be looking for alpha hydrogens, so I'm going to draw those alpha hydrogens in. If it has, if it's a phenol or phenol, depending on how phenol, if it's phenol, I remember the pKa of that is 10, so I'm going to write the pKa of that phenol down. If it is, oh, and that makes it so it can react with regular hydroxides and it doesn't need a super strong one like other alcohols. So that's something that I can keep in mind. And basically just classify your molecule into what it is. If you have a chlorine on something, is that chlorine on just like one carbon connected to one other carbon? Is it a primary? Is it a methyl? Is it, well, it wouldn't be a methyl, but it could be. Is it a primary? Is it a secondary? Is it tertiary? When can we not have substitution happening? I think that is something that I have done throughout the semester in my study habits to just sort of make sure that I am able to see what the problem is for the bigger picture, and just kind of remember what chapter we're thinking back to. So good luck, everybody, and if you need any help with anything, you have until Thursday. We take the ACS at 4 p.m. on Thursday, so we have until then to knock this out, and if we have problems or questions, we can figure them out. So thank you all for a great semester. I love you. Bye!